Hello student, very good morning to all of you. Do you remember what were we discussing yesterday? I think we were discussing about formation of oxazone derivatives, how the oxazone derivative form. So by using as a starting material as a glucose, and generally how many molecules required to form oxazone derivative. So if you use as a 1 mole of 1 mole of phenylhydrazine, and as we know that phenylhydrazine is one of the ammonia derivative, or it is one of the reagent which can give the derivative with carbonyl compound, and as we know that carbonyl compound means the aldehyde or the ketone which containing the carbonyl group, carbon oxygen double bond, generally referred as a carbonyl compound, aldehyde and the ketone. According to as a definition of the carbohydrates, carbohydrates are polyhydroxyaldehyde or the ketone or a compound which on hydrolysis gives a unit is known as sugar unit is known as carbohydrate. Carbohydrates are polyhydroxyaldehyde or the ketone, and as we know that glucose is one of the carbohydrate containing aldehyde is a group, and when it is treated with treated with phenylhydrazine which react with the carbonyl group and produce as a phenylhydrazone derivative. This 1 mole is consumed during the formation of hydrazone derivative, and further another excess amount of the phenylhydrazine when it is utilized, another molecule means second molecule of the phenylhydrazine used to oxidize the secondary alcohol into carbonyl group, and when the carbonyl group is obtained, that carbonyl group further react with third molecule of phenylhydrazine and produce the product that is known as oxazone. Oxazone is a derivative performed with the help of phenylhydrazone, means total number of phenylhydrazine molecule required for the formation of oxazone derivative. The answer of this question: there are 3 molecules of phenylhydrazine required to form the oxazone derivative. Understood this one? So that type of the discussion we already discussed in our previous lectures. So what we are going to discuss today? Now look at here on the blackboard. We are discussing about the basics of carbohydrates. The basics of carbohydrate in that we are discussing today is a Killery-Fissure synthesis. Everybody knows that Killery-Fissure synthesis, Killery and Fischer, those are the name of the scientists. They discovered the method of synthesis of one carbon atom greater or this process is known as step up process. In every carbohydrate, starting from the lower carbohydrate or the lowest carbohydrate, or which we can refer as a starting carbohydrate or starting material, or the precursor or the reference compound generally used as a glyceraldehyde, D-glyceraldehyde. If you start with the D-glyceraldehyde, we can increase step by step one carbon atom in each carbohydrate. Carbohydrate, as we know that carbohydrates, the common name of that the IUPAC name of that glyceraldehyde is aldotriose. Triose indicate that how many number of carbon atom present in that glyceraldehyde. If you count the number of carbon atom, you will find there are 3 carbon atom, and that glyceraldehyde generally is considered as a reference compound, which is a simplest carbohydrate compound which containing aldehyde group as well as hydroxy group. So that is the simplest one, starting from that starting compound D-glyceraldehyde or L-glyceraldehyde. And as we know that L-glyceraldehyde and the D-glyceraldehyde, they are the relative configuration of that carbohydrates, and they are designated on the basis of presence of hydroxy group, whether that and first of all the carbohydrates are represented according to as a Fischer projection formula, and on the basis of that Fischer projection formula, if you observe that glyceraldehyde, the hydroxy group, if it is present on the right hand side, then and then it is designated as a D configuration. When that hydroxy group is present on the left hand side, that is represented by L configuration. L and D are the relative configuration, and how many chiral carbon atom present in the glyceraldehyde? There are only one chiral center present in the glyceraldehyde. Chiral center or the chiral carbon atom means what? The carbon atom carrying 4 different groups, or the carbon atom attached to 4 different groups, that carbon atom is generally referred as chiral carbon atom or the asymmetric carbon atom. So, and when that chiral carbon or the asymmetric carbon atoms are present, that type of the organic compound are optically active in nature, and therefore glyceraldehyde is optically active in nature, and such a type of the isomer they produce, they perform or they give the 2 type of the isomer. They are known as enantiomers. Enantiomer means what? Their physical property as well as chemical property are the same, only they differ in their rotation, means optical rotation are different. One of the compound rotate the plane of polarization right hand side dextrorotatory, whereas another compound rotate the plane of polarization to left hand side. So that type of the isomer are referred as enantiomers. they are non-superimposable mirror images are known as enantiomers, and that we have already learned that kind of the discussion or that type of the thing we already know. So today we are going to learn the Killery-Fischer synthesis. What is the actual Killery-Fischer synthesis? If you remember, as I have already given you the trick how to remember when we are increasing one of the chiral carbon atom in every step, and how we achieved or how we synthesize or how we derived glucose, that is from the arabinose. If you remember that trick, so that time we already seen this type of the thing, but in an actual sense how we are going to synthesize this step of reaction. In every case we are going to start from triose. We will derive tetrose, pentose, hexose. Up to that, another one also we can go on increasing, but that who discovered this step of process, the name of those scientists is a Killery-Fischer synthesis, is a well-known synthesis for the step up reaction of carbohydrate chemistry. So what they did, let us see here the synthesis of carbohydrates. There are two important methods in which an aldose can be converted into different aldose, right? This is the first point you remember, and these conversion can be used not only to synthesize the new carbohydrate but also help to determine their configuration. That is the thing which we are discussing right now. Now in a Killery-Fischer synthesis, this synthesis, the classical method of increasing one carbon atom in the aldose sugar is the Killery-Fischer synthesis. Classical means it is a very authentic method for synthesis of, or it is a classical method of increasing one carbon atom in the aldose sugar is the Killery-Fischer synthesis. Consider the formation of tetrose sugar from a triose glyceraldehyde by this method, which involves the following steps. There are certain steps. If you follow these steps, you are able to synthesize not only the new carbohydrate but also to determine the relative configuration of those carbohydrates. So that is the main purpose of Killery-Fischer synthesis. Number first point you remember, first the sugar is allowed to react with hydrogen cyanide to form cyanohydrin. Cyanohydrin, it is a derivative obtained when we treat aldehyde, or when we allow the aldehyde to react with hydrogen cyanide. The resulting compound formed, the resulting product obtained is known as cyanohydrin derivative. During this reaction, cyanide adds two CHO group and generate a new asymmetric carbon atom to diastereomeric cyanohydrin are produced. So this is the first point where you should remember while discussing about the Killery-Fischer synthesis. First one, again remember the aldose or triose allowed to react with hydrogen cyanide to give cyanohydrin derivative. The two diastereomeric cyanohydrin are obtained. Diastereomeric, you might be knowing that they are differing. One will give you, because here one asymmetric. Let us see as a point number second. These cyanohydrin on hydrolysis with aqueous barium hydroxide give corresponding acids, right? And generate when asymmetric carbon atom, two diastereomeric cyanohydrin are produced, and when that cyanohydrin derivatives further on hydrolysis with aqueous sodium hydroxide produces acids. Number 3 point, the solution of these acids on evaporating to dryness give gamma lactones. Number 4 point you remember, finally gamma lactones are reduced by sodium amalgam. It is a reducing reagent to yield two diastereomeric aldoses containing one more carbon atom than starting sugars. And if we start with L-glyceraldehyde, then we get N-triose and L plus erythrose. Observation. What are the observations they have drawn from this synthesis? Number 1, in the initial reaction with plus D-glyceraldehyde, two cyanohydrin are formed in which the configuration at the carbon atom adjacent to the cyanide group is reverse. Number second observation, second import they have drawn. Likewise, finally, two new sugars obtain D-erythrose and D-triose differ only in the position of hydroxyl OH group at C2, that is the carbon atom adjacent to CHO group. Number 3 observation they have given here, these new sugars do not differ in configuration at C2. The asymmetric carbon atom which was present initially in D-glyceraldehyde. Fourth observation they have given here, the 4 tetros have same sequence of linking of atoms HO, CH2, CHOS, CHOH, CHO. They are therefore stereoisomers, and they are optical isomers and not geometrical isomers. They are stereoisomers and they are not the geometrical isomers. Number 5, there are 2 pairs of enantiomers among 4 tetros. D-erythros is the mirror images isomers of L plus erythros and L plus erythros. Similarly, D plus trios is the mirror image isomer of plus trios. And the last observation they have given, the 2 sugars are related structurally to D-glyceraldehyde because they have the same configuration about the reference carbon atom. So this is all about the theoretical part which we have discussed about that Killery-Fischer synthesis. Let us see the actual, we are going to synthesize some of the compounds starting from D-glyceraldehyde. Let us see here CHO, as we know that the simplest here COH H, and now here is a CH2OH, right? Look at this structure carefully. What do you observe over here? There are 1 chiral center. Chiral center means what? The carbon atom carries 4 different groups, is known as chiral carbon atom, or it is also referred as asymmetric carbon atom. Now look at OH, and this glyceraldehyde, it is a triose. Although triose, the name of this D, why I am putting here as a D, why I am designating as a D, because the OH, when these carbohydrates are generally written according to as a Fischer projection formula, there are definite way to represent, to write the carbohydrate. There are 3 carbon atom, they are in the straight chain. I am writing as a vertically, this structure is written according to Fischer projection formula, and at carbon number 2, this is a carbon number 1, 2 and 3, there are 3 carbon atom. At 2 carbon atom, it is a chiral center, or it is known as a chiral carbon atom because it is attached to 4 different groups. OH on the right hand side, and therefore it is designated as a D-glyceraldehyde, right? This is the D-glyceraldehyde. We are talking about the step up reaction, how we can increase one of the carbon atom, how we can, or how will you prepare tetros starting from the triose. This is a glyceraldehyde is a triose, and now when it is treated with hydrogen cyanide CN, it gives 2 diastereomeric isomers, one which you will get here C triple bond C nitrogen atom cyanide derivative, and here C, then OH I am writing on the right hand side, and this hydrogen, this is a new asymmetric carbon atom develop or produce here. Another one carbon atom, there is no change, we can keep as it is on the right hand side, so I am putting it is as it is, and then second one CH2OH, right? So this is the representation of what we got. This is a cyanohydrin derivative, cyanohydrin cyanohydrine derivative. There are the two possibility of this cyanohydrine derivative. Two are the diastereomeric structure we are getting. Look at here. I am writing that one. Now I am going to put the hydroxyl group on the left hand side, because there are two possibility when cyanide group is going to attach to that carbonyl group CHO aldehyde group. There are the two possibility. It generate two chiral center. It generates one additional asymmetric carbon atom. So one will rotate the plane of polarization right hand side, and one which can rotate the plane of polarization to left hand side. So look at this one. There are also as a two chiral center. These two are the cyanohydrine derivative. Here remember, OH I am putting on the right hand side. Here OH I am putting on the left hand side. So this is the simultaneously we are going to synthesize how we can get as a triose over here. Now let me draw another structure here. CHO, then C, OH, hydrogen atom, and then C, H2, OH. Not this one. Let me draw properly over here. What I am going to write here, HO on the left hand side and the hydrogen on the right hand side. And now this structure, because this and this, they are the enantiomers each other. This is a L glyceraldehyde. Glyceraldehyde. This is the structure of. If you put as a mirror over here, what do you see? They are non-superimposable mirror images of each other, and these type of the structures are known as the enantiomers. There everything is the same except optical rotation are different. Everything is the same means their physical properties as well as chemical properties are the same. So this type, they are non-superimposable mirror images. This type of the isomer are known as enantiomers. Now same treatment I am going to do over here, hydrogen cyanide. Now here also I am going to get two compounds. One is a C triple bond nitrogen atom. Now what I am going to do, I am going to keep this one as it is. Now when the new cyanide group is attached to that carbonyl group, it will produce one chiral center like this, and rest of the thing, this thing I am going to put as it is. Here is a hydroxy group on the left hand side, hydrogen atom over here, and then this one CH2OH. There also has a two chiral center. One additional asymmetric center is generated over here. Here again carbon nitrogen triple bond, then C. Now what I am going to there, two diastereomeric isomer I am going to write over here, HO on the left hand side, and now hydrogen atom I am putting here, and now here this hydrogen atom hydroxyl group I am putting as it is, and this is a hydrogen atom, and then now is a CH2OH. So this the structure which we got after adding the hydrogen cyanide. The resulting compound obtained is known as cyanohydrine derivative. So these are the cyanohydrine derivative which we got over here. Understood this one? First step is a very important step. Whenever we are adding as a hydrogen cyanide, resulting compound obtained is known as cyanohydrine derivative. Understood this one? Now Now, due to the limitation of this blackboards, I am removing this part so that we can write the rest of the structure over here. Now, look at here what I am going to hydrolysis. Now, here I am going to add, that is the barium hydroxide OH twice, that is twice H2O, hydrolysis. This is a hydrolysis process. Hydrolysis. Here also as a hydrolysis, just barium hydroxide OH twice, that is twice H2O. Means how many I should write here? 4 are there, right? So 4 here you can write BaOH twice. Here I am also writing as a BaOH twice barium hydroxide. Barium hydroxide is used for the hydrolysis of cyanohydrin. This is a functional group which is going to convert into as a carboxylic group. What I am going to get over here? COOH, right? Another carbon atom, look at OH on the right hand side, H, then C, OH again on the right hand side, left hand side, and CH2OH. The 2 chiral center which we got is as it is. So this is the acid which we got. This is the acid we got. Here also we are going to get as acid COH, but here they are now look at here, H on the right hand side, hydroxyl group on the left hand side, then OH on the right hand side, hydrogen on the left hand side, and then CH2OH, like this. So look at, if these two are acids which we got, they are what we can call it epimers of each other. Epimers means that the in my previous lecture I already told you that the epimer means what? They are differ in their configuration at only one chiral center. So that type of the isomer are known as epimers of each other. So this acid and this acid, they are epimers to each other. Now I am hydrolyzing this one. So here this remember, this cyanide group is going to convert into as a carboxylic group, and rest of the thing which I am writing over here, they are as it is. This here is a hydrogen atom and HO on the left hand side, and then CH2OH. That's the compound which we got over here, and 2 chiral center in those compounds. Now what, after the hydrolysis of that cyanide group, this cyanide group gets converted into carboxylic group, and the remaining we are going to here H, then HO, then C, here H, hydroxy on the left hand side, and then CH2OH. That is the compound which we got over here. All are the acids, right? These are the acids. Now these acids, as we got here after the hydrolysis of cyanohydrin derivative, we got here as an acid. Now again, as I already told you that due to the limitation of blackboard, I am cleaning first, and now what I am going to do next one will be the just heat it. After heating, there is a removal of water molecule. In every case, here triangle indicate as a heating, and there is a elimination of water molecule. Here also as the same, heating, removal of water molecule from such acids is very easy to remove. Then after heating, there is a elimination of water molecule, and the resulting compound obtained, which we which we know that it is a lactone formation, gamma lactone we are getting over here. Let us see here, C double bond O, then this COH we write as it is, this hydrogen atom over here. Now second carbon atom, here is a OH and this hydrogen now is a CH2, and this carbonyl group and this CH2 they get connected with this ring, and this is called as a, this one is known as alpha, beta and gamma. This is known as a gamma lactone. This is known as a gamma lactone. And as we know that cyclic esters are known as lactones, and if cyclic amides they are known as a lactam. Remember the word over here. Now in this case also what you are going to get, this is the carbonyl group of that acid, water molecule means OH from here and one H from here, they get removed, and rest of the thing here H, this OH on the left hand side, there is a C and OH on the right hand side, hydrogen atom and then CH2. Now this carbonyl group and that CH2 I am connected through this oxygen linkage. So this is known as a gamma lactone again. And now here again what I am going to get here, carbonyl group C double bond O, then this C, OH and hydrogen atom over here, then C, it is a hydrogen atom and one HO is there, and then this CH2, this carbonyl group and CH2 is going to attach like this, and which we got, that is nothing but as a gamma lactone, right? Gamma lactone which we got here. And here also again C double bond O, then here this C hydrogen atom and then HO, then C hydrogen atom and then hydroxyl group over there. Then now this CH2 and this OH now connecting each other, and this is known as a lactone formation. Got it? When this lactone is formed, I think this is a much bigger synthesis, this one. So which we got over here, that is the this one lactone, that is a gamma lactone which we got over here. Now again I am cleaning this one, these structures. Why I am cleaning this structure? As we know that due to the limitation of this blackboard. So let us see further what I am going to get over here. Here just by heating such type of the acid, they get converted into lactone. That is a tendency of this compound, and now this compound further, that is a 2 hydrogen, that is a nascent hydrogen, when it is produced, that is sodium amalgam, right? And that sodium amalgam, it is a reducing reagent which can reduce specifically the lactone, and which is going to convert into as a, this is a Na, sodium amalgam. Same here again I am going to use here nascent hydrogen atom, sodium Ag, that is a sodium amalgam. Here again as a 2H, means this type of the hydrogen atom or the nascent hydrogen atom, sodium amalgam, which I am going to get over here. After reduction of lactone, what I am going to get over here? Here we are going to get as a trio, CH, then this one OH as it is, this is hydrogen atom, this C, OH on the right hand side, hydrogen on the left hand side. Now this CH2 and OH which remains as it is. So there is a one carbon atom is increased. If you number this 1, 2, 3 and 4, there are 4 carbon atom in the straight chain, and that type of the compound is called as a tetrose, right? And now here also what I am going to get, CHO aldehyde, and then this carbon atom H on the right hand side and hydroxyl group on the left hand side. Look at here, OH on the right hand side, whereas hydrogen atom on the left hand side and CH2OH primary alcohol, which is as it is. After reduction of that lactone, gamma lactone, which produce here again as a CHO, then carbon atom OH on the right hand side, then in the carbon number 3 hydrogen atom on the right hand side and hydroxyl group on the left hand side, and rest of the things CH2 and OH over here. Now in the second case what I am going to get, here again as a CHO, then carbon, here hydrogen atom on the right hand side and hydroxyl group on the left hand side, then again hydrogen atom on the right hand side and the hydroxyl group on the left hand side, and then CH2OH. These are the trios which we got over here, and after that trios we will again going to reduce that carbonyl group into further this which we got. These are the this one is the erythrose, erythrose, this one erythrose, and this is a D3-ose, triose, and this one is a, look at hydroxy group on the opposite side, therefore L3-ose, and this one is a erythrose, and after that further pentose, how we will get as a pentose, that we will, I think there is a, I think that we will see in the next lecture. Let us stop today here. Have a nice day. Thank you.